Hi, my name is Lakshmi Soundarya Chakka. Today I'm gonna explain about the linear regression model, which is a statistical technique we use to model and analyze the relationships between a dependent variable and one or more independent variables. Here, our goal is to predict the dependent variable value, which is based upon the values of the independent variables. We have many techniques for evaluation metrics for linear regression models. First we're gonna see the mean squared error. It's nothing but the average of the square differences of what actual and the predicted values. How we calculate it? 1 by n into yi minus y cap I whole square. Here, I value ranges from 1 to n. What is y of I? I previously told you these are the square differences between the actual and the predicted values. So yi is the actual value and yi cap is the predicted value. And here n is nothing but the number of observations. How can we interpret it? What is this MHE is doing? It's helping us to measure the average of the squares of the errors. If it gives a higher weight to larger errors because errors are squared here. A lower MSE indicates it's a better fit. Next, the next we are seeing the root mean square error. It's easy. We already had the value of MSE. What we're gonna do? Just we are using the square root for it. Here, here RMSE is nothing but root mean squared error. What's it doing? It is providing us the measure of the average magnitude of the errors, which has the same units as the response variable. It is easier to interpret, and also lower RMSE value means it's nothing but a better fit. We already know lower MSE is a better fit. And here in RMSE also lower RMSE value means it's a better fit. Next, we are gonna see mean absolute error. Previously what we did, we just square rooted it, right? So here what are we gonna do? Here we are finding the absolute difference between what actual and the predicted values. And same way here I ranges from 1 to n. How can we interpret it as? It's nothing but we are finding the average magnitude of the errors. We are not considering its direction here, and we also need to know it's less sensitive to outliers when compared to MSE, mean squared error. And here again, if we get how lower the value, then we can say it's the better fit. Last and final one, it is r squared. It's nothing but the coefficient of determination. This indicates the proportion of the variation in the dependent variable. That is nothing but the which is predictable from the independent variables. How can we calculate this? R square is equal to 1 minus S into S result by S into S total. Let's see. Here RES means residuals. So nothing but yi minus yi cap whole square, where I ranges from 1 to n. It's nothing but what we are doing here, sum of square residuals. Again, S into SS total. What we are doing here, we are finding the total sum of squares. That's nothing but where y dash is nothing but yi. Here we have it, right? Is the mean of yi. We need to find if we have, for suppose we have 10 or 20 values, how we will find mean? It's the same way as y dash is nothing but is the mean of yi value. And how can we interpret it is basically this r square value ranges from 0 to 1. If we have r square is equal of 1, that means regression predictions perfectly fit the data. If r square is 0, what does means? None of the variability of the response data is around its mean. We also get to know here how these metrics quantify model accuracy and goodness to fit. We are talking that we have seen that lower the value, it's better fit. How it's actually working here, we're gonna see here. First, What we are talking about, MSC and RMSC. We already know both metrics quantify the accuracy of the model by measuring the average squared or maybe absolute error. A model with lower MSC or RMSC is generally more accurate. We are calling it as a better fit, and also RMSC is more interpretable in the context of original data units. And next, MAE. This metric quantifies the accuracy by measuring the average absolute error. It is also useful for us to understand the typical size of the errors, and it is also more robust to outliers when it compared to MSC. Next, R squared. Here, R squared quantifies the goodness of the fit. We are already know, we are already compared it to 1 and 0, what's gonna happen. Here what's it's showing, it is also knows to provide us how independent variable explains the variability of the dependent variable. It's nothing but we are again talking about the good fit again. That's nothing but a higher R square indicates which is a better fit. Let's see with an example here. For suppose I have y, which is the actual values, and y cap is the predictor values. What we know, MSC, it's nothing but the first. We have 3 here. What are we doing? What's the equation we have? 1 by n yi minus yi cap whole square, right? We're gonna do the same. Here we have 4 values. So 1 by 4. Now actual minus predicted, right? 3 minus 2.5 whole square plus minus of 0 0.5 minus of 0 of whole square, 2 minus 2.1 whole square plus 7 minus 7.8 whole square. What we got as the result here? 3 minus 2.5. It's nothing but 0.25. Means here we already square rooting it, right? Nothing but here 3 minus 2.5 is 0.5. Whole square of it is 0.25. I am just simplifying it and saying the answer. So just take a look. You will get an understanding when I'm explaining it to you. And we did the same way for the rest, and we got the answer as 0.2875. What I told you previously, RMSC is nothing but root of MSC. We are doing the same here. Root of 0.2875. It's nothing but 0.536. Next, MAU calculations. What we know, it's the actual difference, right? So what we gonna do? We are gonna 1 by 4. Again, 3 minus 2.5 plus minus 0.5 minus 2 minus 2.1 plus 7 minus 7.8. Again, here we are using modulus, right? So it will be like everything will be positive in the end. So what we got? 0.5 plus 0.5 plus 0.1 plus 0.8. What's the answer we got? Everything's divided by 4 because we have 4 values and 0.475. Next, last the least, which we are already gonna see is R squared calculations. First, y dash is equal to, we have all these values. Let's add those all. 3 plus minus of 0.5 plus 2 plus 7. And we have 4, so divided by 4. It's nothing but we got 2.875. Now, we have to find total. So, what we're gonna do? 3 minus 2.875 whole square plus minus 0.5 minus of 2.875 whole square plus again repeat it, 2 minus 2.875 whole square plus 7 minus 2.875 whole square. What are we doing here? We are separating the actual values with minus actual values minus of y mod, y dash. What we saw previously, y dash is nothing but the mean of y, right? What we did here, it is the same, right? Y dash, what we did, we find the mean of all this, and we for finding the total, what we are doing, let's suppose this is yi minus y dash of whole square. That's what we are doing, right? And this is the result we got. 29.1875. And we need to find residuals, right? We know MSC value already. We have 4 values here. What's that? We are doing 0.2875 into 4. It's nothing but 1.15. Here, we need to find what's the value of r square at the end. What are we gonna do? First, 1 minus 1.15, nothing but SS residuals by SS total, which is nothing but equal to 0.961. That's it. Thank you.